Hello everyone. Today we are going to discuss about the topics covered in week 7. That is some introduction on the uh, XRDs, and I'll be mostly dealing with the concept through questions, and some concepts I will be talking. Uh, if whatever will come in the questions accordingly. So first, uh, distinguish between characteristic and continuous X-rays. So to uh, get into this uh, X-rays, um, as we know, it is coming from the electromagnetic spectrum. So uh, in X-rays also we have different kind of uh, outcomes accordingly the how the primary electron beam is interacting with the material, accordingly what type of X-rays we are getting. So the primary electron, when the primary electron beam the it eject inner shell electron of space whatever specimen we are giving, creating a vacancy in the orbital, and turns the atom uh, into an ion, which we call it as to be in an excited state. So this vacancy is filled when an outer shell electron is transferred to a inner shell, which brings the atom to the ground state. So it's like, a primary electron beam ejecting one electron. Here a vacancy is created, and this vacancy is filled from some outer shell electrons. And when electron is ejected from this shell goes to excited state, and then when it is filled, then it comes back again to ground state. And while doing so, they release energy, and this energy is equal to the difference in the binding energy of these two cells. So this excessive energy is released in form of X-ray photon. So the characteristic X-rays have sharply defined energy values, and they occupy distinct energy position in X-ray spectrum, and they are unique to unique elements from which they are coming from, and distinct energy position of X-ray lines form this basis for chemical analysis, where a different element in a specimen and identified based on the unique orbital transition energy. So we may say this they are unique to element from which they are coming from which and this distinct position of X-ray lines X-ray lines they form basis for a microchemical analysis. What is done here? It is here different elements in specimen material are identified. And in continuous X-rays, the primary electron beam, they sometimes their whatever speed they're moving, they decelerate due to the interaction with atomic nuclei of specimen. And the energy loss due to this deceleration is emitted as photon. uh, because of this deceleration there is energy loss, and they are ejected as photons. And this whatever photons will be getting, those energy can range from 0 to whatever maximum energy we are supplying with the help of the electron. So therefore they form a continuous electromagnetic spectrum. Hence they are also called continuum uh, X-rays, or sometimes called white radiation or Bremsstrahlung radiation also. So this continuum is generated due to combination of all the atoms in the specimen, and they appear as a background in X-ray spectrum. Uh, so as it is not unique to particular element, so they don't have any unique feature, and they are not used in any analysis too. So this the energy loss due to deceleration is emitted as photons with varying energies, maybe from 0 to whatever maximum energy we are providing with the help of electrons, forming a continuous electromagnetic spectrum called continuum X-ray, or it's also called white radiation, or it's also called Bremsstrahlung radiation or breaking radiation. So we can say the basic difference between these uh, two characteristic and continuous X-rays, as one of them provide us unique features of the elements of the specimen whatever we are taking, but the other one doesn't give that information, and they appear as basically a background. So what is the notation used for characteristic X-rays? These X-ray lines are usually denoted by cells from electron, from whatever electron they are ejected. And as we know, different shells are given by K, L, M, and this whatever cells which are there, they are followed by a line group called alpha beta. So if the transition of electron is from L to K shell, then it is denoted as K alpha line, and if the transition is from uh, M to K, then it is called K beta line. Since the energy difference between K and M is larger than between uh, K and L, this K beta is of higher energy than K alpha, and a number usually is written to signify this intensity of line. So the most intense K line is written as K alpha 1, and the most intense L line is written as K alpha L alpha 1. So we so this denote notation which we must have encountered usually, this K alpha. What is this? This is a transition from L to K shell. K beta similarly transition from M to K shell. So here, as you can see, energy difference between K M is greater than energy difference between K and L. So from that we can say K beta has higher energy than K alpha, and for intense line notations, this K alpha 1, they are most intense K line. Similarly for different L and M can be written. So these are very important notations which we will encounter in every uh, XRD analysis. So next is what's the significance of Mosley's law. So what is this Mosley's law? Like it was observed that when the atomic number changes by 1, the energy difference between cells varies in regular steps, and uh, it is observed like when the atomic number changes by 1, the energy difference between the cells varies in a regular step. So this energy is given by this Mosley law. The energy of photon given by as E equals to A Z minus C, where here E is the energy of X-ray line. E energy of X-ray line. A is the atomic number, sorry, A and C are constants. Z is the atomic number. A comma C are constants, and they are dependent on whatever cells they are coming from. Dependent on cells K, the cells are K, L, M, and this Z is basically the atomic number. So this relationship, they describe the energy. This basically describe the energy required. Just a second. This this energy. So this equation, they describe the energy required to excite any series of transition line. So this equation describes energy required to excite any series of transition lines. So for example, X-ray photons of highest energy in an atoms, uh, those are emitted from K alpha cells. So this energy is basically equals the binding energy of 1s electron, which will be proportional to this Z square, and this energy will be different for each element, and hence we are able to identify each unique elements having different atomic number. So next, what is excitation potential? This is basically the minimum energy required to eject one electron from atomic shell, and what are its dependence. So this is uh, uh, this is the minimum energy required to eject an electron from an atomic cell. So how does it depends on different parameters? So how as the size of the atom increases, um, the energy required to excite any particular transition line also will increase. So um, the size of atom increases. What does this mean? This means as the size of atom is increasing, so we are going from lighter to heavier elements. We are going from lighter to heavier elements. So here the energy required to excite any particular transition line increases. Energy required to excite any particular transition line, like those K alphas, L alphas, M alpha, different these are transition lines. Basically transition line also increases. So for example, uh, let's say we will consider two element, let's say K alpha of nickel and K alpha of aluminum. So as this is more heavier than nickel is more heavier than aluminum, so nickels and so this excitation potential for nickel will be higher than aluminum. And again another important point to note here is, as we go from different cells like KLM, accordingly the potential decreases, like the highest excitation potential of K cell, uh, the excitation potential of K cell increases with even small increase in the atomic number, like when we go from let's say mm, copper to zinc, like that the atomic number is increasing, but the excitation potential will be drastically higher. So the excitation potential of K shell increases extensively with increase in atomic, with small increase in atomic number. These are all very important while we are doing XRDs. There, this parameter plays a very important role. Now, define cross section of inner cell ionization. So it is basically the probability of incident beam electron to be scattered inelastically by atom uh, per unit solid angle. So it is the probability for an incident beam electron to be scattered inelastically by an atom per unit solid angle. So this is denoted mostly by sigma or omega, sorry, Q. So so this cross section decreases as the primary uh, energy of electron increases, and it is also lower for element with higher atomic number, as it is related to the excitation energy. So the this excitation energy increases with atomic number, so it is lower for element with higher atomic numbers. So first the cross section decreases as primary electron energy increases, and it is lower for elements with higher atomic number. Why so? Because critical excitation energy increases with atomic number, hence it decreases for the uh, element. Accordingly, we increase when we increase the atomic number. Now, what is X range? It's basically depth of X-ray production within the interaction volume, which we already read in uh, S while reading SCM. It is the depth of X-ray production within the interaction volume what are the different parameters it depends on it mostly depends on like beam energy, critical excitation energy, specimen density. So parameters, it depends on beam energy, critical excitation energy, specimen density. So it is very why it is so important, because we don't want this parameter. For this parameter we don't want to give higher beam energy to the specimen, because it may damage our sample. So that's why these parameters are very important to understand. Like for a particular specimen, uh, what are the minimum requirements, like how much maximum beam energy we can put on a particular specimen. And so so what is X-ray spatial resolution? It is defined as the maximum width of interaction volume generated by electron X-rays that is projected up to specimen surface. And the low atomic number and low density specimen allows deeper and wider electron beam penetration and generation of X-ray lines, which uh, eventually is a shortcoming for a X-ray spatial resolution. So that's why a higher atomic number and high density are mostly beneficial, uh, uh, rather than low atomic number and low density. So it's defined as maximum width of interaction volume generated by electron or X-rays projected up to the specimen surface. So what is the point need to be we need to keep in mind? A low atomic number and low density specimen allow deeper and wider electron beam penetration and generation of X-ray which eventually degrades the resolution. So that's why we need to use high atomic number elements. Degrades the X-ray spatial resolution, which is so we will discuss absorption more at the later end. So this related to that, this is why is mass depth used instead of linear depth. So the use of mass depth is more common than the use of linear depth, because the mass depth eliminates the need for distinguishing different materials because of the different density when illustrating the relation with depth distribution. So that's why we use mass depth mostly instead of linear depth. Because mass depth eliminates the need for distinguishing different materials because of their different densities. And we are looking at the relation with the depth distribution. So this we can correlate with uh, linear absorption coefficient and mass absorption coefficient, which we can recall like linear linear absorption coefficient that was given by mu, where here I is the intensity, so here when X-rays when they encounter any form of matter, they are partly transmitted or and partly absorbed. So this fractional decrease, this is basically a decrease in intensity, this fractional decrease in intensity of X-ray beam as it pass through any homogeneous substance. They are basically proportional to the distance they are covering inside the material, and this is and as they will move inside their intensity is going to decrease. That's why it's given by a negative coefficient. And this we can easily, when we will integrate it, we can easily get the value of intensity as I0, where here I0 is the intensity of incident X-ray beam, intensity of incident X-ray beam, and it is totally dependent as X, this how this linear absorption coefficient, as the atomic number increases, it becomes more and more dense, and this leads to more scattering of the X-ray, and also the which will eventually increase the uh, results X-ray spatial resolution, which is not the case for the lower atomic number. So it's totally dependent on whatever what type of specimen we are using. So but when we replace like this linear absorption coefficient with mass absorption coefficient, so this equation we can uh, otherwise write as mu by rho with just multiplying and dividing one rho, and so this ratio is called mass absorption coefficient. As this linear absorption coefficient is proportional to a density, uh, this mu by rho is a constant of material and independent of physical state. So this is a constant of material, we can say independent of physical state. Why we can say that? Because this mu or rho are kind of proportional, so they kind of cancel out each other in terms of dimensionality. So hence as it is an independent quantity, so we uh, we use it more often than the linear depth parameter. What is the primary mechanism of X-ray absorption? So X-rays are primarily absorbed in specimen by photoelectric absorption. So an X-ray photon loses all its energy to an orbital electron, which is ejected with kinetic energy equal to the difference in whatever photon energy and critical ionization energy is required to eject that electron. So primarily uh, absorbed by photoelectric absorption. Here what happens, and X-ray photon loses all its energy to one orbital electron which is ejected with a kinetic energy equal to the difference in photon energy and critical ionization energy required to eject that electron. Here's one question. An EDS detector has beryllium window which is 8 micrometer thick. How much fluorine K alpha radiation can pass through this window to be detected by the detector? For fluorine K alpha, mass absorption coefficient is given in beryllium is given as 2039 centimeter square per gram. So here we can recall the expression for mass absorption coefficient, right? I equals to I0 e to the power minus mu by rho to x So here one more parameter we need to know is for the density of fluorine. Here density of fluorine is given as 1.848 gram per centimeter cube. So I0 is given as 0 times 1.848 times 8 micrometer, which is 8 into 10 to the power minus 4 centimeter. So dimensionally if we'll check, it is centimeter square by gram, gram by centimeter cube and centimeter. So it's basically dimensionless quantity, and it's given as, we'll calculate this, 0.05. So from this we can say like only 5% of FK alpha radiation will pass through this beryllium window. So which is very less, so we have to think for any alternative. So here this results tell us only 5% of fluorine K alpha radiation will pass through beryllium. Generally phone silently থাকে কে না 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 generally phone silently থাকে আজকে বাই চান্স কি বলছিস Next, to understand reciprocal space and different um, parameters like Bragg's law and Laurent's equation. To understand those, very this concept of reciprocal space is very important. So let me note down some of the uh, important mathematical formulas which needed to understand. And one of first and foremost is this no scalar product, like A dot B is given as AB cos theta, and cross product A cross B is given as AB sin theta. And here in cross product, the order of the vectors are very important. So if we will change the order, then it will be minus of whatever is there, because this is a scalar quantity and this is a vector quantity. In vectorial notation, we can say this A dot B, A B theta and in cross product this is basically out of the plane. Why this is important? Because for any crystal lattice, if you know like what are this crystal lattice, like any of the crystals can be denoted by repeating dots, which are otherwise known as lattices. So this crystal lattice, they can for every crystal lattice we can construct a reciprocal lattice, and many of the characterization tools are done in this reciprocal lattice. So that's why you need to know about it. So let's say we have mm, crystal lattice defined by vectors a1, a2, a3, then the corresponding uh, vectors b1, b2, b3 in reciprocal space, real space, in reciprocal space, this vectors denoted as 1 by v times a2 cross a3 b times, this order matters a lot, like for 1 it is 2 3 2, it is 3 1, like we can say 1 2 3, and we can assign a such cyclical order to this. And similarly for 3 it is 1 2. So what other important parameters is needed to know, like we usually defined in hexadecimal called HKL planes. So in real space, the interplanar spacing is usually given by HKL, and when we consider uh, interplanar spacing in reciprocal space, let's say HKL in reciprocal space, then what is the relation between these two? They are inversely related, like HKL is 1 by this is like only if we consider the length or the magnitude, which we may say. And this DHKL is written in terms of A1, A2, A3 vectors. Similarly, HHKL is defined in terms of B, B1, B2 and B3 vectors. So, as we'll be considering diffraction, and for diffraction we normally use Bragg's law, and so for Bragg's law is in uh, scalar form, so its vector form is usually called the Laplace equation. So to derive that, we need to know the diffraction, how it is expressed in terms of reciprocal lattice. In reciprocal lattice, and let's say we have uh, one X-ray that is scattered by one atom present at O, and this is the incident X-ray, and the diffracted beams are having notation S0, S minus S, So we consider how this X-ray is scattered by atom at O, and how they are affected by scattered by any other atom A present, which coordinate is given by, let's say, PA, PQA2 and RA3. These are the coordinates for atoms which are affected by the scattered X-rays. So here OA is defined as P A cap, Q A cap, and R. So let the incident X-ray, whatever is coming, is having wavelength lambda. So and this incident beam is given by S0, and diffracted beam is given by S. And here this SS0 and this and these 3 points may not be in same plane. They might be in different planes. To determine the condition under which diffraction will occur, so we need to determine the phase difference between the rays scattered by atoms O and A, different atoms. So we know, like, while considering Bragg diffraction at particular, for a particular set of values, diffraction occurs, not for all the planes. That we also again discuss later. So this OU and OV line, they are the wave fronts perpendicular to incident BS0. Okay, this OV and OU, they are wave fronts perpendicular to incident beam S0 and diffracted beam, the perpendicular to both of them. And let's say the path difference is given by delta, then path difference is given by UA plus AV. Let's say these two path it is basically traversing. So these vectors can be written in terms of dot product of S0 plus dot OA plus minus of SA, which is given by S0 minus S0 times OA, where here OA is this one, and if we say negative OA, then it will be having opposite direction from here. This is OS direction, this will be minus OS direction. So normally path difference is given by 2 pi by delta by lambda. here delta we found minus by h0 by so this one is correlated to the reciprocal lattice by we'll write the vectors in reciprocal space b1 b2 and b3 and here if we'll replace this, then this s minus h0 can be replaced by this, and this OA which we have already seen is written in terms of PQ and R. So this path difference becomes minus 2 pi HB1 HKL dot PA1 PQ R given by their dot product. So each of the elements, this B1 will be dotted with A1, B2 A2, B2 with A2 and B3 with A3, and other terms will be 0 because as we know here this dot product, it will be giving us B1 A1 times cos theta. So if the angle between them, here B1 and A1 are in same direction, so the angle is 0. So this two term will only remain. B1 and A2, they are perpendicular to each other. This B1, B2, B3 are perpendicular direction. Similarly A1, A2, A3 are perpendicular to each other in three different directions. So here only HP plus KQ plus LR term will remain and other term will cancel out each other. So here A1 three term will remain. So the condition for diffraction is this vector this end on a point in reciprocal lattice. So for that to happen, this must be, let's say uh, for this s minus s0 by lambda to be satisfying the diffraction condition, this must be in one of the point in reciprocal lattice space. So for this to happen, this must satisfy this equation. So this is the fundamental equation from which both a Bragg law and Lau equation can be derived. So how, let's say if we'll dot A1 with this, then A1 dot HB1 B2 B3, I am only getting H. So similarly for other A2 and A3, So this three equation are called Laurent's equation, and they must be satisfied simultaneously for diffraction to occur. If any of the equation fails, then they will not satisfy, like then no diffraction will be there. Must be satisfied simultaneously. So from this, like how to get the uh, Bragg's condition, for that we need to draw an Ewald sphere where this in this sphere, each and every point in the outline of the sphere, they basically depicts the diffracted point. So uh, if we have a lattice point consisting of different uh, each lattice points depicting different planes, if they will be coming inside the Ewald sphere, then we may say that those points can only be diffracted. So here in this Ewald sphere, let's say we have similar parameters we will assign. This point is in sphere of, like, if we'll compare the sphere of reflection, means if we compare different parallel planes, and here we have seen like how if a X-ray is coming, they are not actually, this is not called reflection but deflection, like when they're deflecting from different interplanetary spaces, this this sphere is basically representing that deflections basically. So here we can see the previous diagram, like this S minus S0, this is bisecting the angle between S0 and S. So we can consider the diffracted beam can be considered as reflected from a set of planes perpendicular to S0, which is parallel to the reciprocal interplanar spacing given by, which was given by H. So this one is a representation of this equation. So the vector S0 by lambda is parallel to the incident beam, and one and here we can see this length is in one in terms of written in terms of 1 by lambda. So that's why we can say this is in a reciprocal space. So and this O is taken as the origin of reciprocal lattice, and all the scaling are done with respect to this S0 by lambda, and this pair of this is a sphere of radius 1 by lambda, we say sphere of radius 1 by lambda. Then the condition for diffraction from this HKL plane is that the point HKL in the reciprocal lattice point uh, P here it touch the surface of the sphere, and the direction of the diffracted beam is S by lambda. And when this condition is fulfilled, this vector OP, which is equal to HKL, and S0 minus is also equal to S0 minus S by lambda, and hence we can say they satisfy this equation. So here one point to note, uh, this diffraction depends on this reciprocal lattice points touching the surface of sphere drawn about C. As we denote in real space this deflected beam as diffractions, so this uh, each point at the surface of the sphere is also called the sphere of reflection or deflection, and which we denote it as the point of diffractions too. And again, like to derive the Bragg law from the same equation, like in the previous drawing we can see here, this is the S vector, this is the S0 vector, and it is bisected by this S minus S0. So S S0 S minus S0. As H0 minus S by lambda is given by H, and H is related to interplanetary spacing as 1 by D, so we can write 1 by D as 2 sine theta by lambda, which is can be written as 2D sine theta equals to lambda, which is nothing but Bragg's law. So from the same equation We have derived the Bragg's law as well as the Laver's equations. So, which of the following is not a part of electromagnetic spectrum? So, in electromagnetic spectrum, what kind of uh, radiations we usually get? We get, like at higher frequencies, we get gamma rays, and then we get X-rays, and these are overlapping. So we have UVs, then visible, then we get IR, then radio waves, and microwaves according. So here uh, gamma rays have highest frequencies and have lowest wavelength, and as it goes from here to here, frequency decreases and the wavelength increases. And this, as we go higher and higher, this uh, wavelength here varies around in terms of uh, meters, and as we go downward, we here in UV to X-rays we get into the order of angstrom level. And with visible light we have the resolution of micrometer, as we have already seen in optical microscope. While discussing about optical microscope, what was the resolution there? That was the micrometers. So here we have X-rays in electromagnetic spectrum, we have microwaves in uh, electromagnetic spectrum, we have UV rays, but we don't have alpha rays. So alpha rays will be the answer. So with increase in the applied voltage, what will happen to the position of the continuous radiation? As we know, this continuous spectrum is due to the rapid deceleration of the electron which is hitting the target. So any accelerated charges, that those emit energy. So here we can say this with increase in applied volt. So yeah, so here two things we need to understand for this continuous radiation. One, like as we had already discussed, these are coming due to deceleration of electron. So not all the electron decelerate in the same way. So some are stopped in one go, and they give up all at once. Other, they take time to stop. So that's why they create a spectrum of energy. and with related to that, whatever will stop in one go or whatever will take more energy, accordingly the wavelengths are also defined. So one important parameter which is defined here is called short wavelength limit, that is those electrons which are stopped in one impact, electron which are stopped in one impact. This type of uh, X-rays coming from this type of stopping will give rise to a photons of maximum energy. Give photon of maximum energy. So as we know, the energy and wavelength are inversely related. So this will give us minimum X-rays of minimum wavelength. So just a second. Equals to C Hc by electron volt. So we can put in the values here. For H it is 6.626 into 10 to the minus 34, 3 into 10 to the 8, and for electrons 1.6 into minus 19, and yeah, we can get the value as 12.4 into 10 to the power 3 volts. So here we can see the relation between the wavelength and the voltage is inversely proportional to V. So here, if a electron is not completely stopped in one encounter, as I was already telling you, so they undergoes a glancing impact which only partially decreases its velocity, and a fraction of this electron EV is emitted as radiation, and the photon produced has less energy than this h nu max which we get for the photons which are stopped at one go. So here, so we can say, with increase in applied voltage, the peak must shift towards left to this side. So why this should happen? As the voltage is increasing, the number of photons produced per second and the average energy per photons are also increasing, and this is the reason for this. Um, Number of photons produced per second and the average energy per photon are both increasing. So from here, another concept we get, like the total X-ray energy emitted per second, they are basically proportional to the area under the curve, this continuous spectrum which we are getting, and they also depend on the atomic number of the target along with the tube current. So that's why the intensity of continuous spectrum is proportional to the area under the curve, the tube current I, the atomic number, and the voltage applied. And this equality is given here. A is the area under continuous spectrum curve, I is the tube current, Z is the atomic number, and V is the voltage applied. And here m is a constant with a value 2 for I don't have a particular reason for why they give this value. So yeah, so when large amount of this background continuum spectrum, which is otherwise called white radiation or Bernstein radiation, when they are designed, so it is therefore necessary to use a heavy metal as a target, and a very for heavy metals the Z value will increase, and again for if we take also give high voltage, this value will also increase. And yeah, so there are certain application to it which we will discuss later in later lectures. So mostly relation relates the frequency of the characterized line to. So what is the mostly relation tells us? Is a relation between square root of frequency with atomic number, where here Z is the atomic number, the frequency, and these are some constants. So here frequency with atomic number. A beam consists of large number of scattered rays mutually reinforcing one another. This we have seen in Bragg's law. Like whatever the diffracted beam is coming out, they basically reinforce with each other to give us a result. So it is a diffracted beam. A plane in the real crystal is represented by, in its reciprocal space, whatever the planes are there in the real space, they are represented by points only in the reciprocal space. The position of atoms in a unit cell affects which among the following characteristic of diffracted beams? As we always talk about the intensity, so uh, uh, if there is a lot of uh, materials are there, like the atomic number, let's say at the atomic number the intensity will go high, and lower the atomic number it will have a less density, and the electron will just pass through it, so the intensity will be lower. So the intensity is the main parameter here. What is the nature of relation between intensity of continuous spectrum and tube current? As we have seen, this relation intensity of continuous spectrum is given as AIZ So here I was the tube current and it has a direct proportionality. Which among the following is the correct statement about mass absorption coefficient? So as we have seen, like mass absorption coefficient intensity ratios is given by e to the power mu by rho and that whatever depth it is going. So here it is as we have discussed already, it is independent of the physical state of the matter. Here lambda SW, which we have just calculated, this depends on the anode current. The voltage which is applied, this is basically the anode voltage. A maximum wavelength that a crystal can reflect is equal to its 2D spacing. That's true, because here from a Bragg's law we can say 2D sin theta equals to n lambda. So for lambda to be maximum, here it takes the maximum value of sin theta, and that is 1. So the lambda value becomes 2D. So the maximum wavelength that a crystal can reflect is basically 2D. It's true. Now, as we have already derived the Bragg's law in terms of reciprocal space, in real space, how it is seen. Let's say we have different planes where for one plane of atoms, let's say we have incident beam 1 and 1A. They strike at atom, let's say at K and P, and they are scattered in all direction, but only in direction 1 dash and 1A dash. Their scattered beams are completely in phase, and so they are capable of reinforcing one another, and in other scattered uh, components, they cancel out each other. Only 1A dash and 1 dash scattered beams from 1 and 1A rays are capable of reinforcing one another, and other scattered rays will be cancelled out. Similarly, the rays that are scattered in the first plane in direction this parallel to 1 dash are in a phase, and they contribute to the diffracted beam. So this will be true for all the planes separately, and now we have to find out the reinforcement of rays scattered by atoms in different planes. So let's say we consider another ray 2 scattered from point L. This the path difference between this 1k1 dash 1k1 dash and 2l2 dash is given by path difference between for rays 1k1 dash and 2l2 dash is given by ml plus ln given by sine theta plus. So this is also the path difference for overlapping rays. Those are scattered by different points. So this is scattered rays 1 dash and 2 dash will be completely in phase if this path difference is equal to a whole number. So that's why we write and this is what is called Bragg's law. So we say like whatever the rays are deflecting from each uh, in planes, though if like only those which are capable of reinforcing one another, they will only sustain and other will cancel out, and they contribute to the diffraction, and this is what we call Bragg's law. It essentially states the condition which must be met if diffraction is to occur. So there are different, like as I was already telling, like on different direction of phase, the scattered beams are out of phase and they cancel out each other, which is we normally called destructive interference. And the rays scattered by all the atoms in the planes are completely in phase, and they uh, they do constructive interference, and for which they form diffracted beam in the given direction. So many people, what they do, like they like, confuse they correlate this diffraction and reflection together, but there is a fundamental difference between two. So difference between diffraction and reflection. The diffracted beam from a crystal is built up of rays scattered by all the atoms of crystal which lie in path of incident beam. The reflection of visible light takes place in a thin surface layer only. So we may say diffracted beam from a crystal is built up of rays scattered by all the atoms of the crystal which lie in the path of incident beam. But this reflection they only takes place in surface layer. And the diffraction of monochromatic X-rays takes place only at those particular angle of incidence which satisfy the Bragg's law, but the reflection of visible light takes place at any angle of incidence. So Bragg's law, but the reflection can take place at any angle of incidence. The reflection of visible light by a mirror is almost 100% efficient, but the intensity of diffracted X-ray is extremely small compared to that of incident beam when they are reflecting. So reflection of visible light by good mirror is almost 100% efficient the intensity of diffracted X-ray beam is extremely small compared to that of incident beam. So there are some different facts related to Bragg's law in terms of geometry, like the incident beam, the normal to reflecting plane, and the diffracted beam should be coplanar, and the angle between diffracted beam and the transmitted beam is always 2 theta. This is also called diffraction angle. So 2 geometrical facts about Bragg's law. One is incident beam normal to reflecting plane and diffracted beam, they are coplanar, and the angle between diffracted beam and transmitted beam is always 2 theta, which is also called diffraction angle. And it is always measured experimentally. The 2 theta which we always see in XRD samples. That is basically the angle between the diffracted beam and the transmitted beam. And there is a very nice boundary condition to wavelength, and that is as we can say, like the value of sin theta cannot exceed 1, so we may say this lambda to be less than 2d. So for most set of crystal planes is an order of 3 angstrom or less than 3 angstrom, which means that the lambda cannot exceed value of 6 angstrom. So if for example, if you take a crystal of wavelength 500 angstrom, they cannot diffract UV radiation. So these are some of the boundary condition on lambda for which what type of radiation can put, or what material we can take, whose if we'll put X-rays on it, what kind of result we can get, that will depend on this parameter. So this is it for today. Meet on next week.